So in terms of the processes of humidification and dehumidification, actually the term of the topic or the topic itself implies what's it all about. Okay. Again, I'll pause recording for now, class. Okay, so as I was saying, so when we speak of humidification and dehumidification, it has something to do with humidity, it has something to do with air, it has something to do with water vapor. Now, we go to the basics first, and that's how the terms that you will be associating these processes to shall be understood. So when we speak of humidification in layman language, if you're going to understand it in a very simple manner, it's just simply the process of adding or putting in moisture or water vapor or humidity into air, or adding it into air. Now, the opposite of such is dehumidification. So as the term suggests, you could see with the prefix D that it is the opposite of humidification. So it has something to do with the removal of moisture in the form of water vapor or humidity from air again. Now, since we have humidification, then it has something to do with humidity. So it is actually the presence of water vapor or moisture in the air. While when we speak of relative humidity, on the other hand, it is the comparison of the actual moisture or water vapor content of air versus to the maximum that it can hold. And that is at a condition we call saturation condition. Now we will go back to this later on when we start again with drying, because these things are very also important in the topic of drying. So humidity is different from relative humidity. So in here now, you more or less have the idea of how to distinguish one from the other. So humidity simply tells you of the presence of water in air in the form of water vapor. But when we speak of relative humidity, as the word relative means, it is measured relative to something. So the current amount of water vapor or moisture in air is measured against its maximum amount that it can hold, referring to air at a particular condition. So that is why it's referred to as relative humidity. Now, in the study of this humidification and dehumidification, we'll be needing the psychrometric chart. So that is why I ask you to have a copy of the psychrometric chart. So if you have your handbook, good, because that's the thing that you're going to use. But there are actually class available psychrometric chart in Google. You can Google it, and the one that I've used here is actually the one I took from Google because it's more complete than the psychrometric chart that I myself, I could speak for that I have been using when I was a student. Complete in a sense that some of the information that I would otherwise solve, I can already read directly from that particular chart. So the study related to the use of the psychrometric chart is what we call as the psychrometrics. So it's used to describe the field of engineering concerned with the determination of the physical and thermodynamic properties of gas and vapor mixture. So the gas that we're referring to in here is most of the time air, and the vapor is water vapor that this air holds. Now we move on. So this is the psychrometric chart that I have mentioned just a while ago. So this is more complete than the psychrometric chart that is available. I hope the psychrometric chart that you have now in the 9th edition is comparable to this in terms of completeness of the information that can be extracted from it. So you can see here, so I chose this one because the lines now are given emphasis in terms of the colors that are being used. So you get to know what a particular curve or line represents in terms of the numbers and the labeling that goes with that particular line. You could see here on the saturation curve, these are referred to as saturation curves. The different curves you're seeing here, the first one is the red one. It's saturation curve because this is 100% relative humidity already. Okay, you can see here on the blue curves, the one in the beginning which has 10%, it's labeled as relative humidity. So as such, you are to view these curves that are in blue ink plus this one that is in red. It's in red class because it's already 100% relative humidity as the relative humidity. So you will use these particular curves later on in answering problems related to the use of the chart and related to, of course, processes of adding moisture and removing water vapor rather from air. Now, what you could see also here is these green lines. You see these green lines, slanting green lines. So this represents the specific volume, okay? Specific volume, and it has values here of 0.79, 0.81, and so on and so forth. So the green line is to be understood to be the specific volume in cubic meter per kilogram for air. Actually, you will learn in the starting slide of the drying processes that this can be solved, even if this is not written or this could not be read out from your psychrometric chart. You can have this solved, okay? The same thing with relative humidity. You can also have this solved. Now, what you have here on the saturation curve, the 100% saturation curve, relative humidity that is, you see the temperatures, the wet bulb temperature. So they are in red. And on these lines, which starts off with the wet bulb temperature, meaning all of these are wet bulb temperature of 20 degrees Celsius. This is for 25 and this is for 30. You also have the enthalpy values. So the enthalpy values at this particular wet bulb temperature. Now, aside from that, you get to see that here on the horizontal axis, you have the dry bulb temperature. And in here on the rightmost vertical axis, you have the specific humidity, rho, omega rather. Now, specific humidity meaning humidity in itself. So it's grams moisture measured per kilogram of dry air. So notice that the way we specify humidity is the amount of water per unit amount of dry air that your air can hold. Now, what about the numbers that you see here on the leftmost portion? This is the dew point temperature. So later on, I will show to you how this particular temperature will be used or how will this be found for a particular given condition. But this is the dew point temperature. So a lot of things are in this curve actually. The key is in understanding the different lines, the different curves, and the values that you see on the horizontal and vertical axis. As you go along using this particular psychrometric chart, you will, shall I say, master on how you're going to find or read out the information that you will be needing. Of course, for now, you will have a lot of things here that you could read and it easily to be and you can get easily confused with that. But as you go along, you will get used to it. Okay, so that's it. That's for our psychrometric chart. I'm sure the one that you have in your handbook is not colored, so it will be quite a challenge to read compared to this one wherein all the lines are having colors and you could see the corresponding line, what is it, and the corresponding value of a particular line. So if a particular value, by the way, for something, for a property that you're going to read from here or a characteristic is not right on a curve or not right on a line, you are to approximate based on the lines or the curves that you are seeing. So if you need to draw a curve here in between so that you would know what is it, what is the value for something when it is 90% relative humidity. So that's it. So the 90% must be somewhere here in the middle of the 80 and the 100. And probably what you have in your handbook has already everything written from the 10% to 100%. So it really depends on the chart that you are having. Now, what are the advantages of using the chart? So as I have mentioned already to you, some of the values that you can read directly from the chart could be solved. And it will be taught to you when we start the slide on drying. So I don't want to discuss it here because it will just be a repetition. So if all the values actually are calculated manually using the formula, it will take a lot of time in terms of recalling the said formula. But with the psychrometric chart, these values can be found within seconds or minutes, as long as, of course, you know where to find it. Now, when the psychrometric chart also, we can easily find the present and the final condition of air. Say, for example, your air is cooled from 100 degree Fahrenheit to 75 degree Fahrenheit. All you have to do is draw the horizontal line to locate the initial and the final condition of that air in the cooling process. Of course, you do not know what is this particular 100 degree Fahrenheit and 75 degree Fahrenheit for now. But nonetheless, class, if a problem is silent about the temperature that is given, when we speak of psychrometric chart, when we speak of humidification and dehumidification problems, when we speak of drying, if the temperature given is not specified to be wet bulb temperature, dry bulb temperature, or dew point temperature, automatically it refers to the dry bulb temperature. So now you know that this one is the dry bulb temperature, and later on you will know where is the dry bulb temperature, because specifically we're going to do the reading one by one from the psychrometric chart for this. Now, a psychrometric chart is very useful also in carrying out heat load or cooling load calculations. Now, wherein you need already to use the energy balance for us to be able to know the heating requirement or the cooling requirement for a particular process. Now, we move on. Now, how do we read from a psychrometric chart? So let's take, for example, you're given values of dry bulb and wet bulb temperatures, which are, let's say, for the dry bulb temperature, you have 78 degree Fahrenheit, and for the wet bulb temperature, you have 65 degree Fahrenheit, respectively. We will find out the values of the other properties using these two given values only from the psychrometric chart. Just like how you do it with the XY axis, what you do, you use the two coordinates, the XY coordinates, and wherever they intersect, then you try to find the value of anything related to the intersection of these two things. So it's the same thing with this. So the first thing that you are to do on the psychrometric chart, you are to locate the value of the 75 degree Fahrenheit on the dry bulb temperature scale rather. It's located at the bottom of the chart that I have shown to you a while ago. Anyway, I will show to you a different chart next to this slide. Then you locate the wet bulb temperature of 65 degree Fahrenheit on the saturation curve. So the saturation curve here is referring to the 100% relative humidity curve. Okay, so we have the blue curves that I have shown to you a while ago. So the saturation curve scale is right on the 100% relative humidity, or the one that is only colored red. Now extend the vertical line, which is the dry bulb temperature, from 78 degrees Fahrenheit, and the diagonal wet bulb line from 65 degree Fahrenheit, and get the point of intersection. Then find out the values of the various parameters at this point. Now, if this particular example here that I've written is shown to you in the form of a particular location in the psychrometric chart, it would look something like this. So you could see on the 78 degree Fahrenheit, for example, this is 78. I cannot, by the way, go back to my psychrometric chart because that one is in SI. So the sample that is stated here is English. So the dry bulb temperature, for example, is 78 degree Fahrenheit. That's on the x-axis. Your wet bulb temperature, you are to locate on the 100% relative humidity curve. So you look for the 65 degree Fahrenheit there, and you are to extend, of course, that line. And this one you are also to extend. So wherever these two intersect, now you will have different values that you can read from the psychrometric chart. So one would be, so if you recall the green line, the specific volume. So what would be more or less the specific volume at this point of at this particular condition of your air? What would be its relative humidity? So this is the wet particular curve or relative humidity curve scale. It will fall into approximately. What is the humidity ratio? You can read directly here on the vertical axis. What's the dew point? You can read here. If you recall, there is this another axis here on the left, which gives you the dew point. at this particular temperature. So what you do, to the intersection of the wet bulb temperature and the dry bulb temperature, you just move horizontally. So this is for cooling, this is for heating. And that's it. So the intersection of the two given values will lead you to a lot of properties associated with this particular state of your air. But when we speak of a process, then it has something to do with, let's say you label this as initial state, and then it is to be cooled to a particular temperature, then this would be your final state. Or it would be heated to this particular temperature, then that would be, it would be just as a case of going left if it's cooling and going right if it's heating. That you will learn later in the succeeding slide. So you just need for now to know how you're going to get the other properties based just on the two that were given. And that's the dry bulb and the wet bulb temperature. Okay, we move on. So the psychrometric properties that actually you can read from your psychrometric chart, I have here 7. So all of this can be read directly from the psychrometric chart. Okay, given the 2, you will know the other 5. Now let's go to each one. So let's define each one so that you have a clearer understanding of what they represent and where they are, on how to read your psychrometric chart or how to find them in your psychrometric chart. So when we speak of the dry bulb temperature, this is to be simply understood as the temperature indicated by your thermometer when it exposed to air in a place sheltered from direct solar radiation. If it's not directly heated by the sun, then the temperature that is registered by your thermometer is said to be the dry bulb temperature. Now, the dry bulb temperature is customarily added to the temperature to distinguish it from the wet bulb, or the dry bulb term is added to the temperature term before it to distinguish it from the wet bulb and the dew point temperature, because you know we have 3 temperatures: dry bulb, wet bulb, and dew point temperature. So the dry bulb temperature can either be expressed in English or as a unit and can be denoted straight by a vertical line on your psychrometric chart. So I have here the representation of the dry bulb temperature. So this is your dry bulb temperatures, all the vertical lines that you see. Everything else is not written here. So when you go to the left, the dry bulb temperature decreases. So it's a cooling process. And when you go to the right, your dry bulb temperature increases, and that's a heating process. When you go up, nothing happens to dry bulb. It's still the same dry bulb temperature. Okay, now we move to the next temperature. So we go to the wet bulb. How do we distinguish the wet bulb temperature from the dry bulb, aside from where you're going to find it in the psychrometric chart? So you have to understand, or you should be able to distinguish one from the other. Excuse me. So when we speak of the wet bulb temperature, it is the temperature recorded by your thermometer when the bulb is enveloped by a cotton wick saturated with water. So the temperature that your thermometer will register when it is enveloped by a cotton wick saturated with water. The accuracy of a simple wet bulb thermometer depends on how fast air passes over the valve and how well the thermometer is shielded from the radiant temperature of its surroundings. So it should not be exposed directly to the sun when this particular procedure of reading the wet bulb temperature is being done. Now, the wet bulb temperature can also be expressed in terms of Celsius or Fahrenheit and is denoted by a straight diagonal line in the psychrometric chart. So this is your wet bulb temperature. As we move up and down along the wet bulb temperature, these are your wet bulb temperatures. I have already shown it to you. The wet bulb temperature does not change, just like the dry bulb temperature when we go up and down, doesn't change. The red arrow indicates an increase in the wet bulb temperature. We know that as we go up, the readings here are increasing. The blue arrow indicates a decrease in the wet bulb when we go down or when we read downwards. But notice, class, that your wet bulb temperature is not read like this, but rather it follows the slant line where it is starting from. So if there's a particular reading scale here, you're going to read the wet bulb temperature in slanting manner, not in downward or not in horizontal manner. Okay, that's for the wet bulb temperature. Now, what about the dew point temperature? So the temperature at which moisture starts to condense out of air is called its dew point temperature. When air is almost saturated with water vapor, the very first instance that you could see the formation of water droplets or water droplets condensing already, that's the when you measure the temperature, that's already the dew point temperature. If you recall a high school laboratory experiment, a simple experiment on this is you expose a particular very thin metal in air, and then you try to cool it at the very instance that there would be the formation of droplets on either side of that plate. You measure the temperature of that, and that's the corresponding dew point temperature. It's the same thing in here. So at that particular point, we say that your air is saturated with water vapor, and that particular time when that water vapor starts to condense out of air, just like when solid starts to crystallize out of solution. So the temperature when that particular water vapor starts to condense is the dew point temperature. So the dew point temperature is also known as saturation temperature because it won't happen in the first place. There won't be any dew that will form on the test, whether it's a watch glass or a metal, if the saturation point of your air water vapor mixture was not reached. So that is why it's called the saturation temperature. Now, dew point temperature is determined by moving from a state point horizontally to the left. Whatever is your state point, for example, in the problem that I gave, you're given the two temperatures, the wet bulb and the dry bulb. So there's an intersection. What you do, you move to the left. It says here, from a state point horizontally to the left along the lines of constant humidity ratio. Wherein it's a process actually wherein it's a constant humidity process until to the left along the lines of the constant humidity ratio until the upper curved saturation boundary temperature is reached. When that happens, what you have already read is the dew point temperature. For it to be clearer, you could see it here. So for your particular state point, let's say you have a wet bulb temperature here, and you have the dry bulb temperature here, and they are in here, then you just move to the left until you reach this one. And you read the corresponding temperature. Of course, it's horizontal, so you're just going to read it here. That would be your dew point temperature. In the psychrometric chart that I have shown, the dew point temperature is written here on this side of your axis, the left vertical axis. In here, what you have is the humidity or the specific humidity. It's so easy to distinguish the three temperatures because dry bulb will be vertical, wet bulb will be slanting, and dew point will be horizontal. So that's the difference of the three. So if you're going to sum up everything, this is your dry bulb, this is your wet bulb, and this is your dew point. So it's not a problem being confused of which is which because they are read differently from the chart. Now we move on. So when we speak of relative humidity, so I partly discussed this a while ago. So the ratio of the partial pressure of water vapor to the equilibrium vapor pressure of water at the given temperature. This definition of the relative humidity allows you to solve it analytically without having to read it from the psychrometric chart. You can only read it from a psychrometric chart, by the way, if you're given the temperatures, let's say wet bulb and dry bulb. If not, you can get this from the psychrometric chart. Let's say, for example, you're just given one temperature. How can you read this from the psychrometric chart? Of course you can. It's impossible because you need at least two conditions for you to be able to know the other five properties that could be read from the chart. So in that case, there has to be an alternative way of finding the relative humidity. And this is it. Just the ratio. You get the quotient of the partial pressure of water vapor to the equilibrium vapor pressure at the given condition. So most of the time, that condition is in terms of temperature. So relative humidity depends on the temperature and the pressure of the system of interest. It requires less water vapor to attain high relative humidity at low temperature, and more water vapor is required to attain high relative humidity in warm or hot air. So relative humidity is dimensionless because we're measuring something relative to another and is usually expressed as a percentage. So when you speak of 100% relative humidity, this indicates that the air is saturated and cannot hold any more moisture. So it holds already the maximum water that it can for a particular condition. Now, preferred values for comfort to us people will be 35 to 60% relative humidity. Beyond this, we'll be feeling very sticky and warm already. So actually 60, well, you already start to feel sticky with this. So I think we'll go for the lower relative humidity measure for us to feel comfortable. Now, when we start the topic on drying, we will be solving problems related to relative humidity wherein it's not read out from the psychrometric chart because you're only given a single temperature. Now, relative humidity, I have already shown to you a while ago. So these are we call this saturation curves, relative humidity curves. And this is how we solve it. So amount of moisture that a given amount of air is holding right now, what is the amount of moisture that it is holding over the amount of moisture that a given amount of air can hold, meaning the maximum amount of moisture that it can hold at that particular condition. So that's why it's called relative humidity. Now, we speak of humidity ratio. What is this? When we speak of relative humidity, it's also in the form of ratio. What about this humidity ratio? So actual weight of water in air to water vapor mixture. If humidity is water in air over kilograms dry air, this one is actual weight of water in air to water vapor mixture, meaning this is the mixture of water and dry air already. So the amount of moisture per unit amount of dry air. Now, most of the time, this is just referred to as humidity, amount of moisture per unit amount of dry air, or some will use the term specific humidity. And this is also dimensionless because both are in amounts. But nonetheless, we try, or I ask my students to really write kilograms, for example, kilograms moisture or kilograms water vapor per kilogram of dry air. Actually, they cannot cancel each other because they are referring to two different parts of your mixture. But nonetheless, if you're going to look at the units that are being used there, it is also a dimensionless quantity. So humidity ratio or humidity or specific humidity, meaning the same thing. Okay, amount of moisture per unit mass of dry air. Now, this is it. The one that we have read a while ago, kilogram of or mass of water vapor per kilogram dry air. So that's the moisture content that you can read on this part of your psychrometric chart. Now, second to the last, we have the specific volume. You know this in thermodynamics. So specific volume of a substance is the ratio of the substance volume to its mass. So it's the reciprocal actually of density and an intrinsic property of matter. Intrinsic in the sense that it's not dependent on the amount of matter that we have. So it's not dependent whether you have a big substance or a small substance. Its specific volume or its density will still be something that is constant. Now, specific volume is defined as the number of cubic meters occupied by 1 kilogram of a particular substance. The standard unit is cubic meter per kilogram. You know that. So specific volume for an ideal gas is also equal to the gas constant multiplied by the temperature and then divided by the pressure multiplied by the molar mass. This is just the reciprocal of the formula for the density of an ideal gas. If it's not an ideal gas, it's okay. You just assume it's behaving ideally, then you can have already the specific volume. And these are shown as diagonal lines on the psychrometric chart, the one that is colored green. So you saw it a while ago with colored green lines, also labeled as green. Now, last is the enthalpy. So enthalpy is usually designated as H, even in thermodynamics, it's designated as that. It is the total amount of heat energy of the moist air in the case of the mixture of water vapor and air, and therefore includes the amount of energy of the dry air and the water vapor in the air. So you will have a formula representation to this at the start of the drying problems that we will be solving in the next or in our last topic for this SEM. In the approximation of ideal gases, lines of constant enthalpy are parallel to lines of constant wet bulb temperature. Thus, the enthalpy is indicated by the diagonal lines on the chart. If you recall the diagonal lines of the wet bulb temperature, we also have there the enthalpy content at that particular wet bulb temperature. So those are enthalpy lines also. And these are the lines. If you're only going to isolate this particular part of the psychrometric chart, so these are the lines that you'll be able to see. On top of these lines are the wet bulb temperatures. Okay, so these are the 7 properties that we can read from our psychrometric chart given the conditions. Now, what about psychrometric processes related to these properties or processes that are dependent on your reading on the psychrometric chart? So we have 5. So we can have sensible cooling of air. And by the way, when we speak of sensible, there has to be a difference in temperature. So sensible cooling of air and sensible heating of air. Then we have humidification. In the process of humidification, it could be either cooling and humidification or heating and humidification. You add water vapor to air, but one process is cooling air, the other one is heating air. Now, in the process of dehumidification, it's the same thing also. It could be either cooling and heating. So both of these processes can happen together. Cooling with dehumidification or heating with dehumidification or vice versa. Then we can also have adiabatic mixing of 2 moist air streams. So when we speak of adiabatic mixing, from the term adiabatic, there won't be any heat loss or heat transfer, that is, to our system that we are mixing. Okay, let's go to this particular psychrometric processes one by one. So when we speak of sensible cooling, this is the removal of heat from moist air without, take note, without the removal of moisture. You just simply cool down the air by removing some amount of energy from it. It allows, or it also follows, a constant humidity ratio on the psychrometric chart. So in the process of simple cooling, actually the same thing with heating later on, when we draw on the psychrometric chart, it would be something that is happening horizontally, because we just simply either decrease the temperature in the case of cooling or increase the temperature in the case of heating, but the humidity which we are reading on, if you recall in our psychrometric chart, the humidity that you are reading on the vertical axis on the right side is kept constant because you are traversing the psychrometric chart horizontally. So how we represent it schematically, it would be something like this. So from state 1 to state 2, you have a process of cooling. We expect that T2 will be lesser than T1. Enthalpy here, of course, will be lesser than in here. And we have a certain amount of heat removed from the system. So that's sensible cooling. The opposite would be sensible heating. So we add on heat to the system. Still the process is constant humidity. So if it's plotted on the psychrometric chart, you're simply going to go from left to right. There's an increase in the dry bulb temperature, but there's no change in the humidity of the system of air and water vapor. So in this case, since we have heating, T2 now and H2 will be greater than T1 and H1 respectively. So this is your state 1 and that's your state 2. Now, humidification, now this is that part wherein you're going to add on moisture. Moisture would be add on to air. So addition of moisture, but take note, Klaus, without the addition or removal of heat. In the case of the first two, the heating and the cooling processes, there's no change in the humidity. It's a constant humidity thing. In here, we add on moisture to air, but there's no amount of heat added or removed. So you could see this as a simple illustration. So moisture is added to our system of gas and water vapor. Correspondingly, that moisture of course will have its enthalpy. So that's HW. And by the way, the H here refers to enthalpy. That's humidification. And we know that processes can either be a cooling humidification or a heating humidification. So you could see here that if it's a heating humidification, heat is added to the system. At the same time, moisture is being added to the system. Of course, the other one is just the opposite of this. Okay? So in this process, specifically for cooling and humidification, moisture is added to air by passing it over the stream or spray of water, which is at a temperature. So this particular spray of water is at a temperature lower than the dry bulb temperature of the given air. So take note of this. When air is to undergo cooling and humidification, the temperature of the cooling water that should be used is lower than the dry bulb temperature of air. I think that makes sense, because how can you cool something when you're going to subject it to a system which is higher, or put it on an environment which is at a higher temperature than itself? So the temperature of the spray of water should be lower than that of air. In the case of heating and humidification, of course, it's the other way around. Addition of heat and moisture, this involves sensible and latent heat transfer. So take note, now it will be having sensible and latent heat transfer. Now, dehumidification, removal of moisture from moist air without removal of heat. So even if we remove moisture from air, we don't remove heat from air. So it could be a cooling dehumidification or a heating dehumidification. So cooling humidification, so you remove what? This time you remove a certain amount of heat to your system, and moisture is also being removed. So Q out, and you see here moisture out. This involves, just like humidification with heating, this involves sensible and latent heat transfer as well. If it's heating and dehumidification, it is the addition of heat and removal of moisture from moist air. Actually, okay, class, I was disconnected. I will just share screen again. Can you see my screen? Where am I? Wait, class, I can't see my screen anymore. Where am I? Not it. Okay. Wait, class. Okay. Share screen. Reset. Okay. Do you see my screen? Do you see my screen, class?
Yes. Yes.
Do you see it? My internet is really
Nadula
very...
naman
Ara naman siya, na ka-unstable. Subong lang man niya siya nagbisyo. Kaina, wala man siya nagbisyo. Now you can see? No?
Miss Arat.
Ara na siya. But there is this thing on my slide. Wait, kasam. Wait. Where was I? Okay. record again. So just let me know if you cannot see my slide. Okay, it's still being recorded by the way. So this is how the processes here could be depicted in the psychrometric chart. So when we have a process of humidification, so amount of moisture increases, so relative humidity increases. So humidification, it goes up. The state or the arrow from one state to another, if depicted on the psychrometric chart, will be from going down up. If it's dehumidification, it's from here going down. If it's cooling, it's going to the left. If it's heating, it's going to the right. If it's heating with humidification, it's slanting upwards. And if it's cooling with dehumidification, it's slanting downwards. So this is how let's say how you're going to plot the points from initial state to final state of your system later on in this process of humidification and dehumidification. And that's how they should be reflected in the psychrometric chart. Now, what about adiabatic mixing of moist air streams? So for adiabatic or evaporative cooling in a psychrometric process, which involves the cooling without heat loss or gain, sensible heat loss by air is converted. So the sensible loss by air is converted to latent heat in the added water vapor. So whatever amount of energy your air losses is converted to an increase in the latent heat of your water vapor. So it's just one part of your mixture giving something, or something is removed from one part of the mixture, that is your air, and it's being received by the water vapor in that particular mixture. So that is why it's adiabatic. Now, if one rejects, the other one receives. That is in terms of energy, the heat energy. Now, adiabatic mixing of moist air streams is a psychrometric process that involves no net heat loss rather, or gain during the mixing of the two air streams. So no net heat loss or gain for this particular adiabatic mixing. And this adiabatic mixing could be represented by this particular process. So you have two streams that you're going to mix. In the process, you are to sum up the products of their mass flow rate and enthalpies. So you are to take rather the sum of the products of the mass flow rate and enthalpies of each stream. So in this case, you have two, so you take the product or the sum of the product of the two. If there's an amount of heat that is externally added, this is different heat that is mentioned there, wherein there is no net heat loss or gain. Meaning, if your air rejects if your air rejects energy, your water vapor is going to receive that energy. That's within the mixture. But this one is external heat added to the system. Then you need really to add it. You need to add it to this particular energy balance equation. But if there's no mention about an external amount of heat added to the system in the process of mixing, then whatever is this MH product here, the sum of MH product here, would also be equated to the summation of the products of MH for the streams that are leaving. This is only in the case if you have, as I've said, amount of heat from an external source, either added to your system or being removed from your system. So in this particular set of slides, these aspects of psychrometrics was really laid down to you, and you see its importance in analyzing conditions that are related later on to conditions of, let's say, heating or cooling, a simple heating or cooling, or a little bit higher than that, which is something to do with humidification and dehumidification already. Now, for tonight, I don't want to really subject you to a lot of problems knowing that you'll be having a quiz. So I'd like you to read on this particular sample problems in Janku, please. I really decided it for you to read because the problems are very, very short. Some are even only 2 or 3 lines. They are very fundamentals in nature, very basic. And I know you can manage if you just read it on your own. They are needed as an intro to later on problems that we will solve concerning the topic of humidification really and dehumidification. So what will happen next Tuesday will be, I will give you around 2 sample problems, on one on humidification and another one on dehumidification. Then we go straight to drying. That way we can maximize the time that we have left for, that would only be for next week, because your Thursday, of course, will be still for drying, and your Thursday evening will be for your second quiz, that is. Okay, so for now, if you have any question, I'll stop recording and I'll be ready with your questions.